Caitlin Bache. I'm an assistant editor at ASHRAE Journal. Thank you for joining us for today's webinar, part of the ASHRAE Journal Supplier Webinar Series. The series provides information to ASHRAE Journal readers and to others about products and technology of interest to industry professionals. ASHRAE does not review supplier webinar presentations. The following presentation has been prepared by Kuul. The subject is efficiency gains achieved by moving to ASHRAE allowable temperature ranges at data centers with direct evaporative cooling. Today's speakers are Sean Barlett and Cody Weeks. Before Sean joined the Kuul team, he worked as a facilities chemical engineer for a hyperscale data center operator supporting critical cooling systems at multiple data center campuses. In addition, Sean has held various engineering, project management, and leadership roles in the water treatment industry, supporting customers in the power, semiconductor, and oil and gas markets. His knowledge includes water chemistry, system design, and operations optimization. Cody has worked at Kuul for 6 years. He has expertise in the data center, gas, turbine, AG, and residential cooling markets. Cody helped develop Kuul's proprietary performance and end-of-life tool and manages a global sales team. He's responsible for developing and executing a global sales strategy, managing a diverse team, monitoring performance, leveraging market and product knowledge, and collaborating cross-functionally to drive sales growth. Cody, the microphone is all yours.
Hey, Caitlin, thank you for the introduction. So thanks everybody for joining us this morning. Again, as Caitlin mentioned, we're going to talk about the efficiency gains that could be achieved by moving to the ASHRAE allowable temperatures, specifically related to the data center industry. So again, in summary, as data center designers and operators look for ways to optimize system operations and meet sustainability objectives, one of the most impactful changes is the move from ASHRAE's recommended temperature range to allowable ranges. Increasing the server inlet temperature decreases the hours per year that evaporative cooling systems will be evaporating water. Making these changes can decrease power and water consumption and increase the life of evaporative media. Now, before we get into the heart of the presentation or the webinar today, I want to go through a quick agenda. So first off, we're going to go through just a background on direct evaporative cooling. So this is just an introduction to the technology itself for those of you who may not be familiar, or for those of you who may need a refresher. Once we get through the technology, we'll talk about some of the components of an evaporative cooling system and get a basic familiarity of those. Once I finish there, Sean is going to take us into the TC 9.9 thermal guidelines. This is going to be the heart of the presentation. We'll talk about the benefits of utilizing the expanded envelopes laid out in those guidelines, and then also additional considerations to take into account when you're looking at these guidelines. Now, at the end of the webinar here, there will be time for questions. So there should be a place on your screen where you can type in and send questions to the team. We will answer as many of those as possible within our time limit. If we do not get to your question, there is an email address at the end where you can forward over to our Kuul support and we can answer the questions from there. So what is a DEC system, or direct evaporative cooling? So DEC systems are also commonly known as direct adiabatic cooling or wet bulb cooling, but the direct portion of the name comes from the fact that there is a direct contact between the water and the airstream that needs to be cooled. So as water evaporates, it changes state from liquid to a gas. So that change requires a large amount of energy to make that change. So with the process being adiabatic, the energy required to evaporate that water is then balanced out by the temperature decrease in the airstream. So the direct contact of air and water really eliminates the need for heat transfer through heat exchangers. So this increases the overall efficiency of the system, especially when compared to, say, a chilled water system. So let's talk about direct saturation efficiency. So the effectiveness, the saturation effectiveness, it's a huge factor in determining the performance of the evaporative cooler. So the extent of which the leaving air temperature from a direct evaporative cooler approaches the wet bulb of the entering air defines the saturation efficiency. So when you look at this process on a psychrometric chart, you can see the inlet air temperature and the outlet air temperature, or overall conditions of that air. So evaporative cooling is a constant wet bulb process. Since the enthalpy and the wet bulb lines are nearly parallel, it's frequently called a constant enthalpy process. However, it is a constant wet bulb process. So on a psychrometric chart, the process is shown between the inlet air and the outlet air points on this chart. So as water is evaporated into the airstream, the dry bulb is lowered along the wet bulb line until ideally it reaches the ambient wet bulb. So during this cooling process, the moisture in the air increases. So you can see that through the increase in the absolute humidity as well as the relative humidity of the airstream. So the efficiency of the media. So we mentioned saturation efficiency earlier, but I want to get into that a little more into detail. So the efficiency of the media is extremely important when looking at system design. So as you can see from this chart, and this is just showing some examples of efficiency readings at a certain feet per minute of air velocity across different depths of media. So what you see here is as the air velocity increases, the efficiency, generally speaking, decreases. Now, there are also other factors. The thicker or higher depth media has a higher efficiency. And so you've got air velocity to take into account, the media depth itself, but also the media design and configuration. So this includes, but not limited to, the total surface area inside the media, the flute angles, the flute sizing. All this has to be taken into account when you're looking at the efficiency of a given piece of media. The next important thing to look at with a direct evaporative cooling system, and why the efficiency is important, is what is the achievable temperature. So that's often the most frequent question we get asked is what is the temperature that this system can achieve, and it depends a lot on efficiency. So you'll see there's a simple formula. So the leaving air temperature can be calculated by the wet bulb depression times the saturation efficiency. So the higher the efficiency, the lower the leaving air temperature. The next most important, or sometimes can be even the most important factor when looking at a direct evaporative cooling system, is the evaporation rate. So the evaporation rate is calculated for a direct evaporative cooling system based on the airflow, the density of that air, and then the change in absolute humidity from the inlet to the outlet. So why is this important? Well, the evaporation rate is extremely important when designing the system because it's a huge factor in determining water usage as well as your plumbing sizing going into the system and how much water that system is going to need as a whole. Now, this is going to come into play later on when Sean gets into the TC 9.9. Now, it's very important not to only look at the evaporation rate, but to also look at total water consumption of the system. So evaporation rate is based on airflow, ambient conditions, heat load, those factors. Blowdown, which has to be taken into account when looking at the total water consumption, is solely based on the cycles of concentration of that water in the system. So those cycles of concentration are based on operational requirements of the system, but also the quality and makeup of the water that you're putting into the system. So maintaining all those values to the recommended levels is going to optimize not only performance, but also the life of the media. The COCs, or cycles of concentration, some of the factors in determining that COC number would be pH, mineral content, the scaling tolerance, and also bacterial requirements. So this is very important to understand when we get into the TC 9.9 discussion. So Sean's going to circle back to this and what total water consumption means when talking about the TC 9.9. So let's get into the general components of a direct evaporative cooling system. So with a DEC system, there are many shapes, sizes, designs. However, all systems contain three main components. So those consist of the evaporative media itself, water supply and water distribution system, and also an air delivery system. So the first part, and arguably the most important part of a direct evaporative cooling system, is the media itself, the evaporative media. So it comes in many different forms, but rigid media is the most common in commercial and industrial applications due to higher performance. So rigid media, there are generally three forms of media. You have a cellulose-based media, which is the most common, however, is not fire rated. You have a fiberglass-based material, which is normally UL 900 rated for use in fire retardant situations. So this could be data centers, it could be government buildings, really anywhere where a UL 900 fire code is required. And then you have a PVC media. So the PVC media, while fairly durable, is also generally less efficient than the other forms of media. So the media is really where the magic happens within a direct evaporative cooling system. This is where the air and the water meet to achieve the evaporative cooling process. So rigid media is usually designed with one flow path of water and one flow path for air. So you'll see in the example here, this is shown as a 45-degree angle and a 15-degree angle. So 45-15 is one of the most common configurations. However, there are other configurations that are used as well. So generally speaking, the water flows down the 45-degree angle to the leading edge or air entering side of the media. So as that water moves downward, it's spread inside the media through internal fiber transport. Now the airflow would enter through the 15-degree angle and move through the media, contacting the water as it passes through and helping the evaporative cooling process to occur. The water supply and distribution section, really the second part to the three common factors in all direct evaporative cooling systems, is extremely important. However, it's often the most overlooked portion of the system. So some type of water distribution system is needed to provide consistent, equal water over the whole top area of the media. So this ensures proper saturation. So without the proper water distribution, the system experiences streaking, decreased performance, and potentially even carryover. The final factor in a direct evaporative cooling system that all systems have in common is some sort of air delivery. So this varies in style and design, but essentially fans are needed in some form to push or pull air through the system and help transfer that air through the evaporative media. So the fans are usually supplied in some sort of redundant form, and the control of the airflow is usually done through either variable speed motors or in some cases dampeners, bypass dampeners, as well as the variable speed motors. So applying this direct evaporative cooling system to a data center, there's a lot of different configurations, but they all share key attributes. So during cooling periods, a large volume of air is brought into the data center from outside. So the air is cooled with the evaporative cooling media and then sent into the data hall to cool the IT equipment and in what is usually referred to as a cold aisle. That air is then exhausted into a hot aisle and then exhausted out of the building. However, it is possible to retain and recirculate a certain amount of air to maintain minimum temperatures in that data hall. So there are occasions during periods of cold weather when it can be operated without the use of the evaporative cooler. So this is commonly referred to as economizer mode or free cooling. So that concludes the overview portion of the webinar. I'm going to turn it over to Sean to get into the TC 9.9.
Thanks, Cody. So now that we all have a pretty good understanding of how direct evaporative cooling works, I want to move into how the ASHRAE recommended and allowable ranges affect operation. So over the past few years, I'm sure a lot of people have seen the headlines where major hyperscalers and colo providers have announced plans to raise their IT equipment inlet temperatures in an effort to increase the efficiency of their facilities. So while what we're talking about is clearly not a new idea, some people have been doing it, we want to take some time and revisit this topic and just give a little bit more context behind these announcements. So we're definitely not in the days where you're going to need a jacket to go inside a data hall. We believe that there's still a lot of facilities out there that are not taking full advantage of the recommended and allowable ranges. So why is this? Facility managers and end users tend to be pretty conservative in their approach to increasing temperatures, and justifiably so. The increasingly critical nature of their businesses is really important to them. Data centers going down for whatever reason at this point is now front page news on CNN. I'm sure everyone's heard some iteration of the saying, I get a pat on the back for saving some power and water, but I get fired if the data center goes down. Well, at the extremes, that's true, though we really do believe that with some careful calculation, there's room for improvement. So before we go much further, I want to take a minute and review what we really mean when we say ranges, specifically the recommended and allowable ranges. So the recommended range is where your servers are ideally going to operate under the majority of operating hours in a year. The recommended range was developed by ASHRAE and selected based on ranges that would optimize reliability, IT power consumption, noise levels, and provide some amount of buffer before reaching the allowable limits. Though the allowable range is where IT manufacturers typically test their equipment to operate. While it may function at these levels, depending on the specific equipment that you have in your facility, it is possible that the performance and reliability of the IT equipment could be diminished. So I think really the most important takeaway from this slide is that equipment should operate in the recommended range under the majority of operating hours in the year. So if you go through the ASHRAE guidelines, it explicitly calls out that the recommended envelope was never meant to represent an absolute limit of air and temperature values. The allowable ranges were specifically created to allow sites to have excursions in excess of the recommended range with the purpose of increasing the use of economization. That being said, any move outside the recommended range is always really going to be a balance between energy and water savings of the cooling systems and deleterious effects that could be created on other factors such as IT equipment energy, reliability, noise, and performance. So the ranges that we were just discussing are set by ASHRAE's Technical Committee 9.9, commonly referred to as TC 9.9. So the first guidelines were released in 2004. And if we look at the psychometric chart to the right, you almost have to kind of squint to see the recommended range. It's very limited by contemporary standards. These were 68 to 77 degrees Fahrenheit and 40 to 55% relative humidity. In the 20 years since the first release of the guidelines, this document, Thermal Guidelines for Data Processing Equipment, has really become the de facto standard for the environmental design and operation of electronics in data centers. So a couple years later, the second edition to the guidelines was released, and one of the biggest changes was the addition of the allowable ranges to support the use of economization. This was a period of time where PUE was becoming an established metric, and it was something that a lot of operators were really focusing on. Now, this is really, I think, one of the big steps in the move from the attitude that colder is better. At this time, you can see that the ranges were called 1 through 4, with 1 and 2 specifically applying to data centers. Fast forward to 2011, the psychometric chart on the right is kind of starting to take shape of what it looks like today. 2 additional allowable ranges for data centers were released, and the data center ranges were renamed A1 through 4. So with the release of the A3 and 4, it expanded the allowable operating envelope that would allow pretty much all locations in the continental US to operate in economization near 100% of the year. And I'd say that this is probably one of the biggest reasons for the rise of chillerless data centers over the past 20 years. So the 4th and 5th editions were released in 2015 and 2021 respectively, and in some ways the changes were smaller compared to previous releases. In 2015, the lower relative humidity requirements were changed after some ASHRAE funded research indicated that the effects of electrostatic discharge were actually pretty limited. In 2021, the guidelines to set the upper humidity range were adjusted to be dependent on the levels of airborne pollutants in the airstream. Also, an additional set of envelopes was released for high density computing. So on the next slide, we're going to demonstrate how these envelopes affect cooling hours in a couple different locations. So what we've done here is we've estimated cooling hours based on dry bulb temperature and a small increase from the outside air to the IT equipment inlet to account for some factors like port containment and increase through your fans. So you can see we've got about a half a dozen different common data center locations. So outside of the hottest regions of the year, or hottest regions of the United States, your places like Phoenix and getting into Texas, cooling hours can really be brought down to about 1,500 hours or less when the recommended temperature envelope is used. The number of cooling hours is really going to be dependent on the local climate conditions throughout the year, as can be expected. Another benefit of going with an increased envelope potentially is offsetting increasing local temperatures. So the values that we used for this analysis were based on historical ASHRAE bin data, though as I'm sure many people have noted, every year we seem to be seeing more and more extreme temperatures. So another benefit of going to higher temperature envelopes is potentially offsetting some of these increased cooling demands. So I know one of the big things that we wanted to talk about is water savings. So as Cody went over, the calculation for evaporated water is fairly simple. So we can estimate the amount of evaporated water at a facility if we apply a heat load. So right now we're looking at a theoretical facility with about 7.5 megawatts of IT capacity. So pretty intuitively, the volume of evaporated water is going to track with the cooling hours. Though the specific evaporation volume is also going to depend on a number of other factors like the wet bulb temperature of the ambient air. And I think the big thing to really highlight here is that typically a direct evaporative cooling system is an air side economized system where water is only going to be used during cooling hours. So this is in contrast to a system, say a chilled water system with a water side economizer that's going to be evaporating water constantly. So if we look at the evaporated gallons per year estimates, you can see once you start moving into the allowable ranges for a lot of the locations, especially more mild locations in the mid-Atlantic, out in Central Oregon, and even in the Midwest, your evaporated water drops to almost zero. So what's the reason why the water savings are so impactful? And a lot of that has to do with the way that you're saving water. So if we look at a system operating with a proposed 3 cycles of concentration, For every 1 gallon of evaporation that you save that 1 gallon, plus you save a half a gallon of blowdown. So this is in contrast with the typical water reduction strategy on a evaporative cooling system that involves increasing the cycles of concentration. So when you increase the cycles of concentration, you get a diminishing return. What we mean by that is when you go from 3 to 5 cycles, you get a 16% decrease in your makeup water, though increasing an additional 2 cycles only yields a 6% increase. And the reason for that is that when you increase cycles of concentration, you're really only reducing the blowdown portion of your makeup, whereas cutting cooling hours and cutting evaporation cuts your evaporation plus your cooling hours. So just to be clear, we're not trying to say in any way that cycles of concentration should not be optimized. That's something at Kuul that we do spend a lot of time in working with customers to create custom projections for their specific water and operational parameters, though it just needs to be kept in mind that after about 5 or 6 cycles of concentration, your returns are pretty low. It does increase the chances of scaling, and you create a more concentrated blowdown, which in some locations can cause issues with discharge permits. So if we look at a specific example, say a facility located in Columbus, Ohio, with the same 7.5 megawatts of IT capacity operating at 3 cycles of concentration, if we move from what we're calling, say, a legacy temperature limit of about 75 degrees to even just the high end of the recommended, that change is going to decrease makeup water by a projected amount of about 63%. If the facility is allowed to go up to the A1 limit, it's projected that makeup water could be reduced about 97%. While this is definitely an extreme example, it shows the power of completely eliminating evaporative days. So if we dig into this location a little bit more and look at some ambient temperatures in a more mild month like March and a hotter month like July, and look at the diurnal temperature charts, we can see that for the mild month, even if the temperatures are at the 90 percentile, the outside air would be below the upper range of the recommended temperature envelope and not require any cooling. So in this case, no active cooling, you're just pushing ambient outside air into the facility. Now, when we look at a substantially hotter month like July, you can see that about 8 to 12 hours of the day, the temperature is going to be expected to be over the recommended range. If this system was allowed to operate up to the A1 range, then cooling would be required up to about 7 hours a day. Though this is really the year, when it's looked at over the whole year, the hours in excess of the recommended range are potentially going to be 10% of your total hours or less. So if we tie this back to the definition of the recommended range, which recommends operating within these values for the majority of the year, you can make the argument that the system is going to be within those recommended limits for the majority of operating hours. So while we just went over a number of benefits of increasing the temperature and humidity limits, there's definitely a number of factors that must be considered. While increasing your temperature envelope is almost certainly going to result in a substantial decrease in water usage, power consumption at the IT equipment level can increase under certain circumstances. So why is this? This is really 2 factors. Potentially the fans on IT equipment spinning faster, and also an increased leakage current in your silicon processors. So looking at some average industry data, going from 75 degrees upper limit to the recommended envelope could increase your power about 1 to 5%, while airflow could increase from 10 to 50%. Though, given the large variance in possible power and airflow increases, given the specific equipment, it's really important that these things are confirmed for the specific equipment used in a given facility. So if we look at the overall facility power changes, a lot of that's really going to be dependent on the control strategy utilized. So there's a lot of different options for control strategies. There could be a facility that maintains a constant pressure drop throughout the data hall, or there could be a control strategy that maintains a constant IT equipment, inlet temperature, or hybrid systems, or something in between. Though it is undoubtedly true that most systems will see an increase in airflow and therefore cooling power consumption when ambient temperatures increase. Though for both the facility and the IT equipment, the ambient temperatures are going to be cool for the majority of the year, so periods of power increase consumption will really only be limited in many locations. And one way to help optimize the system is to allow your temperatures to vary over the widest range and allow the cooling system to operate in the most efficient manner when conditions allow. So depending on how your fan speeds are set, allowing them to operate at the lowest frequency during the majority of the year is going to conserve power. Another benefit of increasing your humidity envelope is having a very wide humidity envelope is going to potentially reduce the need for humidification and dehumidification equipment to operate. So probably one of the biggest things that comes up whenever anyone starts talking about increasing the temperature and humidity envelope is, what is this going to do to the reliability of IT equipment? So to help assess the relative failure rate of IT equipment at different temperatures, there was something called the X factor that was developed by ASHRAE. So this is a factor that was baselined off of 68 degrees Fahrenheit IT equipment temperature, as they were assuming that there'd be some use of reheat to maintain a minimum temperature. But there's a couple really important factors that need to be considered when looking at the X factor. So X factor values assume a constant operation at that temperature. So if you want to use the X factor and assess how it's going to apply to a facility, it really needs to be a time-weighted average, not just looking at a single data point. So if we go back to our Ohio example, even if you allow the system to operate, say at the upper limits, the A3 envelope, the majority of the year, the outside air is going to be cooler than 68 degrees Fahrenheit. So you get a time-weighted X factor of less than 1. Though if you had a facility where your X factor was greater than 1, say 1.4, it's only going to increase the number of failures. It's not going to create a 40% failure rate. So if your baseline was 5 failures per 1,000, your failures would increase to about 8 per 1,000. So as Cody mentioned, the media in a direct evaporative cooling system is really one of the most critical components. It's your main source of air and liquid contact. And this media does need to be replaced periodically. It's typically due to scale buildup or the breakdown of the media substrate. Though it's really important to understand that the life of media is really most affected by wetted cooling hours, not just calendar years. So if you are able to reduce the number of cooling hours, wetted hours, operators will have the ability to increase media life or operate at higher cycles of concentration. And the potential increase in cycles of concentration really comes from the fact that a lot of direct evaporative media systems are operated in a intentionally controlled scaling mode. So you're operating intentionally over the saturation value of a lot of salts, and you're basically just trying to scale it slowly. So if you have less hours per year and you're expecting the same calendar life of media, you can potentially increase your cycles of concentration and get a further reduction in water consumption. So while data halls are definitely not continuously operated spaces, they are spaces that humans do have to go into periodically. And raising the temperature and humidity envelopes does change the conditions that personnel have to work in. Another factor is that raising the temperature, as we noted, can increase the fan speed, which increases the noise. So this is really something that the specific risks for your facility and the changes that you're trying to make do need to be evaluated by a qualified EHS representative to understand the consequences of what's happening. And just to kind of add some final thoughts to this, well, we've definitely highlighted that there's a potential for large efficiency gains. This is definitely not a change that we would say should be taken lightly. Before any of the envelope changes are made, it's really an opportunity to look at your facility and see, are there other improvements that should be completed first? So things that should likely be looked at first are, is the containment in your facility as good as it can be? Are all of your drives on variable frequency to allow them to operate at the lowest power consumption whenever possible? Is your control system based on temperature control, and is that as optimal as it could be? Because if these things are done first, it's really going to increase the effectiveness of the envelope changes. Because making this move, it's really going to be a complex multivariable optimization process. That being said, there's a lot of organizations out there like ASHRAE that have detailed guidance documents which can assist organizations with this decision-making process. Though everyone that looks at this change is really going to have to determine if the benefits outweigh the costs for your specific situation. And really, one of the final notes that I want to leave with is that making this change is likely to affect pretty much every stakeholder in your organization. So as we said, there's personnel concerns, so that's going to be EHS. This is going to affect the cooling equipment, so your facilities team, your site services team who manages the server, your hardware engineering team that designs and specs your servers, even your IT equipment vendors. So this is really a process that everyone should be involved in as early as possible, so they can voice their concerns, their questions, and make sure that everything is heard out and mitigated as much as possible.